At this point, we've already looked at electric field created by a positive charge, and we found a nice way to draw that, and the electric field created by a negative charge, and we drew that in a similar manner. But what if we were to have a positive charge and a negative charge, or say two positive charges, really just more than one charge in close proximity to each other? Both of them would create electric fields in the same area. So which electric field would win out, or would we end up with an electric field that's sort of a combination of the two? That's what we're going to look at today, with electric fields created from multiple charges. First of all, let's consider two positively charged particles. And let's look at what the field might be like created by these charges. And for now, we're not going to write anything permanently. We're just going to sort of do some sketching. So the field created by this first charge on the left would probably look like this. Remember, electric field goes in the direction the force would be on a positive charge, right? So if I put a positive charge over here, it would feel a push away from this positive charge in that direction. So that's why our electric field points away from a positive charge. Now, if I were to draw the electric field created by this other positive charge and ignore the existence of the first one, I get something similar. Now, what we need to know is that electric fields, just like other vectors, will combine together. They'll add together as vectors. For example, right here in the middle, I have one electric field that's going to the right and one electric field that's going to the left. And right in the middle where they sort of overlap, they will basically cancel each other out completely, and there will be no electric field there. Up here, I have a different scenario. I have one electric field that's going up and to the right, and one that's going up and to the left. So where they combine, you can imagine if I added those two vectors together, head to tail, I would get some. They both agree that it should be going up, so they have upwards components. But one has a right component, one has a left component. The right and left components would cancel out, and I just end up with this upwards part. So the electric field over here would really, if I look at both of them combined together, would look like that, would be straight up. Now the electric field over here on the left side of my screen is mostly just due to this left charge. The charge on the right does create an electric field way over there on the left, but it's very, very weak, so it wouldn't have much of a contribution at all. So let's erase these sketch marks, and we'll draw it together what the actual electric field would look like when it's completely combined from both of these charges. So over here on the left, the electric field looks basically like it would from just the first charge, because the second charge over here is quite far away. It won't have a big effect. Now, up here, though, things start to look a little bit different. When I'm really close to this charge, where the electric field is very strong from that charge, electric field does exactly as I would expect it to do from that charge. But as I get further and further away, the effect of this charge down here is much less. So the effect from this charge over here becomes more noticeable. And that's why that arrow starts to sort of curve away a bit. Similar thing kind of happens down here. And we get this sort of curving away behavior happening more and more as we get closer to the other charge. Now I can draw the field lines coming from the second charge. Again, if I'm close to that charge and far away from the first one, I can pretty much ignore the effect of the first one. But as I have a field line that gets away from my charge on the right, then the effect it feels from the charge on the left is more and more noticeable, and it'll start to curve. So that gives a good picture of the electric field that would be created from two charges combined together. And we see, as we kind of said before, in between the two charges, right in the middle, the electric field is zero. There are no field lines here whatsoever. And if I stay kind of in this region right midway between the two charges, the electric field there basically points either straight up or straight down. Because the left and right components, one charge pushing to the right versus the other charge pushing to the left, cancel each other out, and we're just left with the up-down components. Now, if we instead want to consider two negatively charged particles, we get the exact same picture, but the arrows are reversed. You might recall when we drew the electric field created by a positive charge and the electric field created by a single negative charge, the pictures were exactly the same except the arrows were reversed. So we get the same thing here. So that's what the electric field would look like as created by two negative charges. Again, the field lines, the bodies of the arrows look exactly the same. The only difference is all the arrowheads have been reversed. Here we see the arrows go away from the positive charges. And that makes sense because remember, electric field is the direction the force would be on a positive charge. If I put a test positive charge anywhere on this page, it's going to feel pushed away from these charges. So that's why the arrows go away. And over here, again, electric field points in the direction the force would be on a positive charge. If I put a positive charge anywhere on this page, it's going to see these negative charges here, and it's going to be attracted to them. So it will feel a force towards them, which is why all these arrows here are going towards the two source charges. Now, there's a couple key things to note about electric field lines now that we've drawn these two pictures. One thing to note is that electric field lines can never cross each other. And indeed, we notice that doesn't ever happen in any of these diagrams. They got a little bit close, maybe sort of over here. It seemed like they might be getting close to crossing, but they never do. If they did cross, if we pretend, for example, we had, this electric field line continued off like this, and then this one continued off like this, and they crossed right there in the middle, I'm basically saying that if I put a charge there, it would feel a force in two different directions at the same time. It would feel a force this way, and it would feel a force that way. And that makes no sense. We can't have a charge feeling two net forces at the same time. An object can only have one net force. Therefore, the electric field can only be going one direction at a time. And that's why electric field lines can never cross. We also see that the electric field lines always start at a positive charge and end at a negative charge. Our first diagram shows my electric field lines starting at these two positive charges. And my second diagram shows electric field lines always ending. The arrowheads go towards and end at negative charges. It turns out, if you were to follow one of these lines over here that starts at a positive charge and continue it out of this diagram, out into the universe, eventually, somewhere in the universe, that electric field line would find a negative charge, would go towards it, and would end at it. So even though we don't draw the start and the end of every single electric field lines, they all start at a positive charge somewhere in the universe, and they all end at a negative charge somewhere in the universe. Similarly, on this side, this line here, I've shown ending at my negative charge, but in reality, it would kind of continue on forever, coming from somewhere else in the universe that I haven't bothered to draw, and that somewhere else in the universe where it originated, where it started, would have been at a positive charge. So sometimes when I draw these arrows, I draw them so the lines kind of fizzle out, or they seem to kind of come to an end. These ones here too, I didn't really draw them continuing out forever, but they would. And if we followed them, eventually they would take us to a positive charge where they started from. So electric field lines can never cross. They always start at a positive and they always end at a negative charge. Okay, let's try one that's a little trickier. Two charges with opposite polarity. So one positive and one negative. So again, it can be kind of useful to think of this. Again, electric field lines go in the direction the force would be on a positive charge. So let's just do some sketching for now. If I placed a positive charge over here in the middle, it would feel pushed by the charge on the left and pulled by the charge on the right. Okay. So I would maybe expect an electric field going towards the right. If I put a positive charge over here, it would feel pushed this way by the charge on the left and pulled this way by the charge on the right. So the overall effect would be that it would probably feel a force kind of in this direction. How about up here? If I put a positive charge up here, it'll feel pushed by the charge on the left, but pulled by the charge on the right. So if I add those two effects together, one going to the right and up and one going to the right and down, the net effect is it should be feeling a force to the right. So up here at the top between the two charges, I should have electric field lines going to the right. Down here at the bottom between the two charges, I should have electric field lines going to the right. And directly between the two charges, I should have electric field lines going to the right. What about if I go closer to one charge or the other? So if I go really close to this charge on the left, say over here, the electric field from the positive charge will be way stronger than the electric field from the negative charge. So I can pretty much ignore the effect from the negative charge, and this guy would just feel a push that way. Similarly, if I go over here, really close to the negative charge, and I put a positive charge there, it'll really only feel the effect of the negative charge. The effect of the positive charge will be minor in comparison, so this guy will feel a really big push or pull towards the negative charge. So over here, I should have electric field lines going up. Over here, I should have electric field lines that go down. So let's try and put this all together and draw a picture of what these field lines would look like. Over here, they're going up. But then in the middle between the two charges, they're going to the right. And over here, they're going down. It goes up here, it goes to the right in between the charges, and it goes down on that side. We can kind of continue this pattern to draw some field lines in the rest of this space here. Directly in between the two charges, my field lines will just go like that. And we can kind of continue this idea as we go around. So that is what the electric field looks like. It's created by two separate charges, in this case with opposite polarity. And at every point, the electric fields from the two different charges combine together to create one electric field, shown here in blue. So let's see if we can look at some example problems here. What is the strength of an electric field midway between a 2 microcoulomb charge and a 4 microcoulomb charge that are 0.6 meters apart? Well, let's draw this out. Here's a charge that's 2 microcoulombs. And here's a charge that is -4 microcoulombs. And they are 0.6 meters apart. Okay. Now what I might actually do is I might add some colors here. I'm going to make this 2 microcoulomb charge, I'm going to change that, and I'm going to make it green. And my -4 microcoulomb charge, I'm going to make that one red. Okay. And if I'm looking at a point midway between them, it'll be right over here. I want to know what the electric field looks like there. So there are basically two components or two parts to this electric field. There's the electric field, there's the part that comes from the green charge and the part that comes from the red charge. We'll call this guy charge A, the green one, and we can call the red one charge B. So, because charge A is a positive charge, electric field lines will go away from it. So at this point here, I would expect it to create an electric field going in that direction. And that's the electric field from A. But if I look at the electric field created by B, the part of the electric field that comes from B, what would I expect there? Well, midway between the charges, I would expect the electric field to go towards this negative charge. So again, I would have an arrow going the same direction. And in fact, I think this red arrow would be a bit longer than the green one. Because this red charge here has a higher magnitude, 4 versus 2, compared to that green one. So this is the electric field coming from B. Now, in reality, if I go there and I measure the electric field, I won't see both of these. I won't see the red part and the green part. I will just see one electric field that will be both of those combined together. So let's figure out what they each are separately, and then we can combine them together. So the electric field from charge A, well, electric field, the formula for the electric field created by a charge is KQ over R squared. So if we plug some numbers in here, the charge creating this electric field is 2 microcoulombs. And the distance I would be when I'm at this point here from that green charge, from charge A, is 0.3 meters. So that gives me an electric field strength of 2.0000 times 10 to the 5 newtons per coulomb. Okay, how about the this red field, or the field created by this red charge? Let's calculate that too. So the electric field created by charge B can also be found using the same formula. And this one is 4.0000 times 10 to the 5 newtons per coulomb. Remember, when I'm using this formula, I do not put in positives or negatives for the charge Q. Even though this charge is a negative charge, I did not put in a negative number. And that's because this formula does not, even though electric field is a vector, this formula does not tell us the full story. This formula is only useful for the magnitude of electric field. So I don't bother with any positives and negatives. That's the reason why there's no vector hat on top of this electric field here, because this formula only tells us the magnitude. So this formula, only for magnitudes. It'll only tell me the magnitude of the electric field, and I should only put in the magnitude of the charge. However, I did use the fact that this was a negative charge already. I used that up here when I drew the electric field going towards it. If that had been a positive charge, I would have drawn that electric field going the other way. So we're not ignoring the polarity of the charge. We're just using it when we draw the field, but not when we calculate the field's magnitude. So I have found the strength of the electric field, of the part of the electric field caused by the green charge. And I have found the strength of the part of the electric field coming from the red charge. But I am being asked not for the two parts, but just the strength of the electric field. Not one part, not the other part, just the strength in general, which means I need to combine those two together. So we can do that right in the middle here. So the electric field strength total is going to be the electric field that comes from A plus the electric field that comes from B. So if I take this number here and this number here, and I add them together, I'll get my result. Now note, when I'm adding these, I'm adding them like vectors. So the total electric field is a vector. The electric field from A is a vector. The electric field from B is a vector. So plus and minus matters here. So when I put in the electric field from A, I'm going to put it as 2 times 10 to the 5, but it is going to the right. So I'm going to put that in very intentionally as a positive 2. And then when I put in the electric field coming from B, it is 4 times 10 to the negative 5, and it's going also to the right. So I'm going to put that in as a positive number. And then I'll end up, when I add those two together, getting a positive number. Which means my answer is to the right. So this was a fairly straightforward 1D example of electric fields. Every electric field I was looking at was going in the left-right direction, so I could simply convey direction by using positive and negative numbers. Let's look at a scenario where we have a 2D electric field, where I can't just use positive and negative numbers for direction. That'll be this one here. So again, I have two charges. One positive, one negative. And I'm looking at this point. There's nothing actually at this point. We're just calling that's just a location in space. We're calling that location Z. And I want to know what the electric field looks like there as created by both of these charges. So let's start by taking a similar approach to what we did in the last question. Let's call this charge up here charge A. That can be my green charge. And so that is a positive charge. So electric field lines will be going away from that charge, right? Other positive charges would be pushed away from it. So if I just look at that charge, the electric field created by it down here at point Z should be going in that direction there. Now let's look at the other charge. We'll call this charge B. It is a negative charge. So that means electric field lines will go towards it, right? If I had a positive charge somewhere around it, that charge would feel a force towards charge B. So over here by point Z, I would have an electric field going to the right as caused by charge B. And now what I'm going to try and do here is combine these two parts of the electric field together to find the resultant or total electric field, which is going to look like this. Electric field is a vector, so when I add electric fields together, I add them as vectors, head to tail. Okay, so we're going to start by finding this part, and then finding this part, and then we can probably do a little Pythagoras to find the total electric field. So the electric field created by A is going to be KQ over R squared. I'm not going to bother writing out K anymore. I think we all know what it is. I'll just leave it as K to sort of save some space. Again, I don't put plus or minus in this formula. This formula is just for magnitudes. And so when I'm at point Z, down here, the distance from point A is, or from charge A is 6 meters. This gives me a strength of 3,000 newtons per coulomb. So let's look at the electric field created by B. Again, in this formula, for the formula of the electric field created by a charge, I don't use the negative sign. This formula is only for magnitudes. I used the negative sign already. I used it when I was deciding which way to draw this arrow. So I used it in deciding the direction. It's not necessarily necessary for finding the magnitude. Okay, so now that I know those two electric field strengths, I can kind of fill them in on my diagram. And we're ready to solve for the total electric field, the combination of those two, this blue guy. So I think I'll be using Pythagoras to find the magnitude. And the direction, remember the direction of a vector is always defined from its tail. So I'll be looking for this angle there. And I can probably use tan to find that. And then to find theta, I can say that tan of theta is 3,000 divided by 3,556. And that leads me to theta is 40.2. Okay, so I have the magnitude of the total electric field. I have the direction of the total electric field. Let's just write those two out together. So the total electric field with a vector hat, because it's combining both magnitude and direction, is 4,650 newtons per coulomb at a direction of 40.2 degrees. And we're not really sure if this is an up, down, left, right problem or a northeast, southwest problem. Let's assume this is sort of a map we're looking at, and so we can call that angle south of east. So the big idea is this. When I have more than one charge creating an electric field in an area, the electric fields created by each one individually combine together. And I can use that idea to find the total electric field. Each one on its own creates an electric field that is a vector. And if I add those vectors together, head to tail, like I always do for adding vectors, and find the resultant, which goes from start to finish, I will find the total electric field at a given point due to both charges combined. And that's exactly what we were drawing over here on this page. All these blue arrows we drew, those were the combined electric field, the total electric field from both of the charges together. One thing I'm realizing here is that in this first example, we actually gave a little bit more information than we needed to. We were asked for the strength of the electric field, which really means the magnitude. So in our final answer, which was down here, 6 times 10 to the 5 newtons per coulomb, we didn't need to actually say that it was to the right. It is to the right, but we were only asked for the strength or the magnitude, not the direction. So we gave a little more information there than we needed to, but that's totally fine. So now let's look at one follow-up question to this example we just finished working on. Remember here, Z was not an actual object. It was just a location in space. And electric fields can exist just in empty space all around objects. But now we're going to make that location a little more interesting. We're going to suppose that a proton is placed at point P. This should say point Z. And we're going to ask what its initial acceleration would be. Okay, so now we have a scenario where I have a positive charge, it's a proton, and it's sitting at this location where there is an electric field going in this direction. And we know that when you place a charge in an already existing electric field, it feels a force. In fact, there's a formula just for that scenario. And it looks like this. This is the formula for the force on a charge in an already existing electric field. But then we're asked, so we know we have some way of finding out about the force on that charge. We're also asked about its acceleration. So how can I take the information about the force on that charge, which I can get from this formula, and figure out an acceleration from it? Well, that's going to be using Newton's second law. F equals m. Okay. So let's see if we can piece this together. If I take a proton and I put it at this point, Z, it will feel a force. So I'm going to need to know the charge of a proton. Remember, protons and electrons have the exact same charge. We call it the elementary charge. Only for a proton it's positive. For an electron it's negative. And what I might do here to just save myself a little bit of work is I might just combine these two equations together right off the bat. So the net force on this proton is going to just be the electric force that we calculate from this formula over here. So Q times E. Okay, so Q is the charge on the proton, 1.6 times 10 to the negative 19 coulombs. And remember, in this formula, because I do have vector hats, I am going to use positive and negative numbers. So this proton is very intentionally a positive charge. Remember, protons are positively charged. Now, the electric field that it's in is this guy here, 4.6 or 4,650 newtons per coulomb, 40.2 degrees south of east. Now the mass of a proton we can look up, and that's 1.67 times 10 to the negative 27 kilograms. And then there's my acceleration. So what I'm going to do here is I'm going to take this vector and multiply it by this scalar. I'm multiplying it by a positive number, so that means it's just going to get a little bigger or a little smaller, but it won't change its direction. And then I'm going to divide it by this number here, which again will change its length, but not its direction. If this proton had instead been an electron, then I'd have a negative number here. And when I multiplied this vector by that negative number, the direction would change. Instead of south of east, it would be north of west. But because we're dealing with positive charges, the force is in the same direction as the electric field, and the acceleration will be in the same direction as the force, so they're all going in the same direction. And if I crunch through all of this and I solve for the acceleration, I get 4.46 times 10 to the 11 meters per second squared. 40.2 degrees south of east. Or in other words, same direction as the electric field. So, what's happening is, because of these two charges, I have two sort of different electric fields, or parts of an electric field that are created here, like this and like this. But because there can only be one overall electric field at a given point, those two pieces combine together so that at point Z, I have an electric field that looks like this. If I then take a charge and I place it at that location, I have a charge in an already existing electric field. It will feel a force. And because positive charges feel forces in the same direction as the electric field, a proton placed here will feel a force in that same direction, sort of down and to the right. And because it has a force on it, it will then accelerate also in that same direction. So if I took a proton and I place it here at point Z, it would accelerate in this direction at 4.46 times 10 to the 11 meters per second squared. That's all for this lesson. The key sort of overarching idea here is that electric fields are vectors. So when you have more than one electric field in the same area and they combine together, you add them just like you would add any other vector, head to tail, and then using Pythagoras or trigonometry to find magnitudes and directions.